Welcome back to CS520. In this session, I'm going to talk about implementing the event loop. The interface, in other words, the public functions for manipulating the event loop, are given here. First, there's a constructor of sorts, a create event loop. It creates an object to store the state and returns back to us a handle, which is just a void star that will pass into these other functions to identify which event loop the other functions apply to. Once we've created the event loop, then we can actually start the event loop executing. So again, we have the first parameter is the handle. You can only start an event loop that's already been created. And then a function and an argument. The function is the initial function to be executed by the event loop, and it takes a single argument. In effect, you can think of this function as the initial handler for the start event, if you will. And all of our handlers are single argument functions. We can also register events. Again, first parameter is the handle, which event loop we're talking about. Second parameter is the name of the event that we want to register. And the third parameter is the handler function for that event. The fourth function in the interface is announce events. So when an event occurs, we can announce it by, again, providing a handle for an event loop, providing the event name. So unfortunately I use different strings for this parameter. They're really the same. It's the event name here. And then an argument to be provided for this particular occurrence of the event to the handler for the event. Finally, we can shut down the event loop, and we can clean up the memory associated with a particular event loop state. So part of the challenge of doing this implementation is, again, struggling with function pointers. If you're not familiar with those, so in C we can declare a function pointer in the following way, right? It's pointer to a function. Notice the parentheses here are introduced to emphasize that the pointer dereference is going to happen first. Again, this is the key to understanding C declarations, is that they mimic the use of the defined identifier. So if we declare a function pointer, we would use it by dereferencing the pointer to get a function, and then the parameters, the parameter list here, indicated by the open-close paren, indicates a function call. So the declaration mimics that. So we parenthesize it to emphasize it's a pointer to a function. It takes a single void star argument, and it returns void. So this is the prototype for our event handlers. Right? They take a single void star parameter. They return nothing. Single void star parameter is modeled on POSIX threads, which have the same sort of interface for that, for incoming arguments. Right? If you have more than one thing, then you have to pass in a pointer to a struct containing multiple things. Our handlers, though, unlike POSIX threads, do not return anything, so they're just void functions. Okay, when I call a function through a function pointer, I can do it this way. I can deref the pointer and then call it, which again mimics the declaration syntax. But C actually lets me get sloppy and treat a function name the same as a function pointer. So I can actually call a function pointer. If func is a pointer to a function, I can call it by just simply saying func paren x paren. So C lets you go back and forth there. All right, let me back up and just emphasize what's an event name. Event names are just strings. So in the two functions where we describe events by name, register event and announce event. The middle parameter here. These are char star. These are just strings. So the event loop, when it's presented with those strings, it will make a copy of the name before registering the event internally. So the user can reuse the memory that those strings are in. A minor point, but something, it's important at the interface to understand these issues. Who's responsible for the memory when allocated structures are passed in across the interface? All right, so let's take a look at each one of these in turns and outline what has to happen. So create an event loop is going to have to allocate some kind of memory block, some kind of object to maintain the state of the event loop. What's in the state of the event loop? Well, the most important thing fundamentally is there's a queue. Right? The queue stores functions and arguments to be executed. And when we create the event loop, this queue is going to be empty. But we have to initialize a data structure to be prepared to enqueue functions and arguments. By when I say functions, I mean function pointers. And queue also, of course, will have to dequeue things. And it's a FIFO queue, right? Things that go in first are going to be retrieved first. Well, there also has to be an event registry. There has to be some way to map event names to event handler functions. This is the whole point of registering events, right? When we register an event, we present a name and we present a handler function, and those are tied together. And the registry has to be able to retrieve the handler functions when it's given the event name at the time that an event is announced. Again, this event registry is initially empty. We're going to also have to have a mutex and a condition variable because the event loop itself is single-threaded. It's just one thread repeatedly pulling a function out of the queue and executing it. However, it can be interacting with a different thread. A different thread can be generating events. So this means we have contention for the state of the event loop. We have multiple threads potentially touching the state, so we need to have a mutex to control access to the state. In other words, the function queue and the event registry. And also, the event loop might run out of work to do. The queue might empty, and at that point, the event loop, the thread running the event loop needs to block and wait for a event to happen. So we'll use a condition variable to block the thread executing the event loop when the queue is empty. So the last step then, after create event loop is initialize the state, is to return the pointer to the state as a handle. So this little opaque object that we create to keep track of the queue, the event registry, and mutex and condition variable, we just return it back to the user, but they don't know what's inside of it, right? They just see it as a void star, and that's their handle for manipulating this particular event loop. Okay. Once an event loop is created, then we can actually start it. And again, when we start an event loop, we have to give it an initial function and an argument for that initial function. So it's sort of if you think about it, it's the main function for the event loop. Here's where we start. Or another way to think about it, as I mentioned a moment ago, it's the handler for the start event loop event. So what does start event loop need to do? It inserts the function pointer with the argument into the queue. Notice the queue always has both the function to be executed and the argument to pass to that function. Those are bound together. So it puts that into the queue, and then it starts the event loop. And what is the event loop itself? It looks like this in pseudocode, right? While we're not terminated, we're going to dequeue the function argument pair that's on the front of the queue, And then we're going to call the function with the argument. And then go back and get the next one. However, we have to have some way to terminate this. We'll talk about this in a little bit. So there's also a checking, are we ready to terminate or not? Notice that the start event loop function will not return until the event loop is terminated. So, start event loop itself actually runs the event loop, and the function does not return. Again, this emphasizes that the event loop, and at least in this implementation, is single-threaded. Right? We're just using a single thread to execute the event handlers one after the other. And we're executing the handlers in the order that the events occur. Okay. But that's not to say that there aren't other threads out there generating events. Okay, but the event loop itself is running single-threaded. Okay, what about registering events? So this is basically registering a handler for a particular named event, right? Again, we pass in the handle for the event loop, the name of the event, and the handler function that we want to have handle that particular event. And all we do here is we insert the name with the associated function into the registry so that in the future, when that named event occurs, we can locate that function and execute it. Okay. Notice that there's no argument presented at the time we register, right? The argument is presented by a particular occurrence of the event, and it's passed at that time to the function. All right. When an event occurs, then there's a call to the event loop to announce the event. Again, a handle is passed indicating which event loop, the event name, and then the argument that should be passed to the event handler for this occurrence of the event. So announce event has to look up the event in the registry. If it's found, it places its handler with the argument on the end of the queue. Okay, so it takes the argument from the third parameter and it puts it with the function that was found in the registry as the handler for this event. It puts that pair at the end of the queue. And if the event is not found, then the system will report an unhandled event. But the system will keep running. Okay, so that's those two routines are the guts of the system, right? Once we're up and running, then we're registering event handlers with register event, and then events are being announced or when they occur by announce event, and that causes the handler functions to be executed by the event loop. Okay. Some point then we're ready to shut down the event loop. So there's a function to do that. Stop event loop, pass it the handle, the event loop you want to stop. And what this should do is it causes the event loop to terminate when the currently executing event handler returns. So there may be a slight delay when we do the stop event loop. The handler that's executing will finish what it's doing, and once it returns, then the event loop itself will terminate. That was sort of indicated when I had the pseudocode here for the event loop, right? We dequeue, we execute, and we execute this to completion. Then we come around and we check, should we be terminating or not? Okay, so the termination comes in the middle of this handler executing, then we will actually terminate the loop, the event loop, after the handler finishes. Okay. And this design for this system actually we're requiring that stop event loop itself be called from a handler function. So it's not allowed to be called from a different thread. This is just to simplify our task of terminating the event loop. Again, as I've said, the event loop is single-threaded. It's just executing functions, handler functions, one after another in the order their events occurred. So if stop event loop is executed from a handler, then there's no race condition. It's, you know, we're doing stop event loop, and then we will finish the handler that contains the call to stop event loop. Then we'll check for termination. So we don't have any tricky race condition to consider there about, for instance, terminating before we block because we think the queue is empty or something like that. Just simplifies the task that we have to do to implement the event loop. But it's important to remember that in our system, we're requiring stop event loop to be called only from a handler. Okay. All right, the last function in the interface is just to clean up the state. Again, we probably malloc a little block of memory to keep track of the queue, the registry, and so forth. And of course, the queue itself may have allocated memory to keep track of entries in the queue, and likewise for the registry. So cleanup event loop is called simply to reclaim any memory that was used by the event loop. Okay. One minor note here is if we're using joinable threads, which if we use the POSIX default, that's what we're going to get. One other thing we need to do is actually, let's skip that. That has nothing to do with this. This is a single-threaded event loop, so we're not worried about that. Never mind. Getting ahead of myself there. All right. Again, just go back to emphasize there's potentially asynchronous calls here. Register event and announce event could be called by another thread. You know, one thread is executing the event loop. Another thread is running asynchronously to the event loop and calling register events and announce events. Therefore, that's why we need to have a mutex to protect the state of the event loop, because there could be concurrent access to the state via the functions in the interface, in particular register event and announce event. And let me repeat something I said before. What do we do if the queue gets empty? That loop is running. We come around the loop and we look and there's nothing in the event loop to be done. And the thread executing the event loop should be blocked. And we'll use the condition variable for this. And who will wake it up? Well, next time an event occurs, announce event needs to signal that condition variable just in case the thread executing the event loop is blocked. All right, one last minor point is that the arguments that are passed in by announce event and then actually pass the handler function when the handler function is executed, those might be allocated blocks of memory, but the event loop itself doesn't pay any attention to the allocation or deallocation of those arguments. That's completely up to the user, the person using the event loop, to worry about. So the event loop is not going to deallocate those arguments, for instance. We just pass them through. Okay. So I think that summarizes what needs to be done to implement the event loop. So let's stop here.